backups are only defensive if you can restore them. In this grepwise tutorial, we build a real restic workflow on a fresh Debian target. Encrypted repository, first backup, incremental backup, snapshot listing, restore test, integrity check, retention, and a system timer skeleton. Nothing here is simulated output. Every terminal scene runs real restic commands against real files. The evergreen pattern is simple. Keep the repository encrypted from day one. Back up a clear source directory. Change data and take another snapshot to prove incrementals. Then restore into a separate path and run a check before you trust retention. Automation comes last after the manual path is proven. Restic can store repositories on local disks, SSH, SFTP, S3 compatible object storage, and several cloud backends. The commands in this tutorial use a local repository because the capture target is disposable and self-contained. The defensive habits are the same for remote storage: encrypt before upload, restrict credentials, monitor failures, and test restores from the same backend your production system uses. We start from a clean target and install restic with quiet apt output. The version command proves the binary is present before any repository exists. In production, you would also pin packages through your normal patching process, but the backup workflow itself starts with a small verified tool install. Now we create actual demo data and initialize an encrypted local repository. The password is stored in a root-only password file, so every later restic command can run non-interactively without printing the secret. The init output is restic's real repository creation message, including its generated repository ID. Secrets are part of the backup design. A password in shell history is a long-term incident waiting to happen, so automation should use a protected file, a secret manager, or a short-lived environment injected by your scheduler. The example password here is intentionally a demo value inside a throwaway container. For real systems, rotate access, back up the secret separately, and document who can decrypt the repository. The first backup stores the complete source tree as a real restic snapshot. Watch the summary. Restic scans files, packs data, and prints a snapshot ID. That snapshot ID is the handle you would use later for point-in-time restores, audits, and retention decisions. Next, we change the source and back it up again. Restic is content addressed, so unchanged chunks are reused while new content is stored. The second summary is the important proof. A new snapshot ID appears, but the added data is small because this is incremental and deduplicated. Snapshots are the restore catalog. We list the repository and see the real IDs, timestamps, host, tags column, and paths. This is the operator view you check before restoring: which snapshot exists, what path it contains, and whether the most recent point in time is the one you want. A backup is not complete until a restore succeeds. We restore the latest snapshot into a separate directory under TMP, then list the restored tree. The source path is preserved under the target, which is why the files appear below TMP restore/srv/data. A restore drill should be boring. Pick a clean target, restore the snapshot, compare the expected paths, and prove an operator can find the files under pressure. Do not restore over the live source during a drill. That hides mistakes and can turn a test into data loss. Clean restore targets make evidence clear. This file came from the snapshot, not from the live system. Integrity checks are part of the runbook, not an afterthought. Restic check reads repository metadata and verifies structure. For this tutorial repository, the real result is no errors found. On production repositories, schedule checks carefully because large remote stores can take time and bandwidth. Retention is where backup systems become dangerous. Deleting old snapshots may be correct, but only after you understand legal retention, ransomware dwell time, restore point objectives, and repository health. Start with conservative policies, keep logs, and do not combine first-time retention changes with first-time prune on the only copy of critical data. Retention deletes policy-expired snapshots, and prune removes unreferenced data. Here we keep the last two snapshots, which means both tutorial snapshots remain, but Prune still runs against the repository and reports its real work. In production, test retention on non-critical data before automating deletion. Automation comes after the manual restore path works. We write a real system service and timer to disk, then cat the files back so the unit contents are visible. The service uses the password file and the same repository path as the manual commands. This is a skeleton to adapt, monitor, and alert on, not a fire-and-forget backup strategy. The finished runbook is defensive and repeatable. Create encrypted repositories with a protected secret, backup real paths, list snapshots, restore to a clean target, run check, apply retention carefully, and only then automate with monitoring. If restore tests are missing, you do not have a backup system. You have a hope system.